Again, this is to welcome you back for today's class, Cisco Instructor Training class. We're going to be looking at Module 9 today, which is FHRP, FHRP Redundancy Protocol. Okay, and we're going to be looking at this topic to explain the concept of redundancy in default gateway of your network, especially when you are running a switched network. So end devices are typically configured with a single default gateway. If I have my computer and I check my IP address, I get a default gateway. Now the default gateway is that single point where all my traffic goes out to when they are going out of my local network. Okay, so this occurs even if a redundant router or layer 3 switch that could serve as a default gateway exists. So first hop redundancy protocol are mechanisms that provide alternative default gateways in switch networks where two or more routers are connected to the same local area network. So if you look at this image, for instance, this is a particular network, and I have PC1 here. This PC1 here has a default gateway. The default gateway probably is router 1. And so if router 1 is down, that means this particular PC cannot reach this server because this particular router interface is down. So the concept of first hop redundancy protocol is that you set it in such a way that even if this particular interface is down, this PC will change its route to forward it to this particular router in order to get to the server. So the whole idea is to give router redundancy. So one way to prevent a single point of failure at the default gateway is to implement a virtual router. To implement this type of router redundancy, multiple routers are configured to work together to present the illusion of a single router to the host on the local area network. So the point we are making here is that you create a virtual router, not a physical router, and that is going to be the default gateway, even though you have two physical routers. Okay, so that particular virtual router will not go down. So irrespective of whichever physical router interface that goes down, that particular virtual router still remains active. And so your traffic, your packets are still being routed. So by sharing an IP address and a MAC address, two or more routers can act as a single virtual router. The IP version 4 address of the virtual router is configured as the default gateway for the workstation on a specific IP version 4 segment. So when frames are sent from host devices to the default gateway, remember, when you use default gateway is when your traffic is going out of your immediate local network. All right, so if it's going out to anywhere outside your immediate local network or your VLAN or whatever, then it needs that particular gateway. All right, so the address resolution protocol returns the MAC address to the virtual router. Frames that are sent to the MAC address of the virtual router can then be physically processed by the currently active router within the virtual router group. So a protocol is used to identify two or more routers as the devices that are responsible for processing frames that are sent to the MAC address or the IP address of a single virtual router. So a redundancy protocol provides the mechanism for determining which router should take the active role in forwarding traffic. Okay, remember, you have two or more physical routers, and one of them is active, one of them is a backup or is redundant or is on a standby. So the virtual one that you create is the one that your local host or the end device always has. So that one doesn't change. All right. So here we are saying that The redundancy protocol provides the mechanism for determining amongst those two routers which one should take the active. So the ability of a network to dynamically recover from the failure of a device acting as a default gateway is known as first hop redundancy. Let me take that again. The ability of a network to dynamically recover from the failure of a device acting as default gateway is known as first hop redundancy. So the concept here is that we want to create redundancy. So if the network is able to dynamically change or switch over to the alternative router, that is what we're talking about. So there are steps to set up this failover. First is when the active router fails, the redundancy protocol transitions the standby router to the new active router role as shown here. So here you see that I have these PCs on this particular local area network. And within this local area network, I have two physical routers. Look at this router here and then this router here. They are the two physical routers. This one here is just a logical router. It's not a physical router. Okay? So these two routers, physical routers, have connection that we have to the LAN segment. So the whole idea is that each of these PCs is going to get a default gateway. Probably this or this interface could be its default gateway. But what the system will receive is just the IP address of the virtual machine. So one of these two routers is going to remain active. The other one will be on standby. But at no time will this virtual IP address change. So once this particular PC sends any traffic or packet going out of its network and it comes to this particular virtual router, the redundancy network failover happens at this particular router, virtual router, to determine which of this particular is active, which one is passive or standby. So if this is the active one, it comes here and then it goes here and then goes here. If this particular goes down, then it comes this way and then goes out. So the standby router stops seeing the hello messages from the forwarding router. The standby router assumes the role of the forwarding router, all right? And then because the new forwarding router MAC assumes both IP version 4 and the MAC. Look at it here. Link or device failure. If this place fails, is this link fails or the device fails, then standby router becomes the forwarding router. Okay? So that is how the FHRP works. Now, when you are configuring the FHRP, you have different options when setting it up. Now, let's look at it. The first one is Hot Standby Router Protocol, HSRP, Hot Standby Router Protocol. And we say that this HRSP is a Cisco proprietary first hop redundancy protocol that is designed to allow for transparent failover of a first hop IP version 4 device. Okay, let's take note of this transparent failover. HSRP is used as a group of routers for selecting an active device and a standby device. All right, this active device is the device that is used for routing packets, and the standby is the device that takes over when the active device fails. All right, now the second option is for IP version 6. All right, and it is the same thing for IP version 4, but this time around it runs for IP version 6. Then the third one is virtual router redundancy protocol. This is a non-proprietary election protocol that dynamically assigns responsibility for one or more virtual routers to the virtual router redundancy protocol, all right, on the IP version 4 LAN. This allows several routers on a multi-access link to use the same virtual IP version 4 address. So in a VRRP, VRRP configuration, one router is elected as the virtual router master, with the other acting as the backup. So the whole idea is to have what? Redundancy. Third one is FHRP version 3. This provides the same thing of version FHRP that we looked about for IP version 4, but this time around it provides it for IP version 6. So it provides support capability for both version 4 and version 6. Then you have the Gateway Load Balancing Protocol, GLBP. All right, BP, sorry. Gateway Load Balancing Protocol is a Cisco proprietary FHRP redundant protocol that protects data traffic from failed router or circuit like HSRP and FHRP. Also, while allowing load balancing. All right, so this is one of the main advantage of GLBP. It does load balancing between the routers. Okay, and then GLBP for IP version 6, that one does for IP version 6. Then ICMP router discovery protocol, and it actually allows IP version 4 packets, allow IP version 4 hosts to locate routers and provide IP version 4 connectivity, all right, to other IP network. All right. Now, Cisco provides HSRP and HSRP for IP version 6 as a way to avoid losing outside network access if your default router fails. So HSRP is a Cisco proprietary FHRP that is designed to allow for transparent failover. So the HSRP ensures high network availability by providing FHRP redundancy protocol for IP hosts on networks configured with an IP default gateway address. So the whole essence here is that we don't want to allow chance for any failure whatsoever type. So whatever kind of failure, we don't want to give chance for that kind of failure. That is when we set up FHRP redundancy protocol. So the role of the active and standby routers is determined during the HSRP election process. So between the routers that you have, there are certain metrics that they use to determine who becomes the active router and who becomes the standby router or the backup router. Okay, so by default, the router with the numerically highest IP version 4 address is selected as the active router. So look at this, for instance. You have this router 1. It has an IP address of 172.168.10.2. Now look at router 2. It has 172.168.10.3. So if you look at 172.168.10.2/24, you look at 172.168.10.3/24. This is the one with the virtual machine. Okay. Now with this IP address, 10.2 is lower than 10.3. So by default, it will go for what? 10.3 will be the active router by default. But if you set priority, okay, look at it. The priority here for router 1 is 150. And then the priority here for router 2 is 100. So the election process looks at the priority first, okay? And the priority here is 150, which automatically makes this guy higher. And so this guy becomes the active router. So he said, however, it is always better to control how your network will operate under normal conditions rather than leaving them into chance. So HSRP priority can be used to determine the active router. The router with the highest HSRP priority will become the active router. So by default, the active router for router 1 becomes the active router because it has a higher priority. So to configure the router to be the active router, use the standby priority interface command, because by default all of them have a default priority of 100. So if I come to standby priority and then I have between 0 to 255 and I give a particular priority value higher than 100, that takes the precedence. Okay. So by default, after a router becomes the active router, it will remain the active router even if another router comes online with higher priority. To force a new HSRP election process to take place when a higher priority router comes online, preemption must be enabled using the standby preempt command on the interface mode. So preemption is the ability of the HSRP router to trigger the re-election process. So if I have a particular network, and as it is now, I have 150 here as a particular router, I have 100 as a particular router for the priority. This is now my priority. If I add another router, physical router, and I give it a priority of 200, for instance, this particular router still remains my active router unless or until I run the preempt command to force the routers to withdraw the election process so that they can determine. So preemption only allows a router to become the active router if it has a higher priority. So a router enabled for preemption with equal priority but a higher IP version 4 address will not preempt an active router. Alright, so that is what we are talking about. So with preemption disabled, the router that boots up first will become the active router if there are no other routers during the election process. Okay, so what are the different states of the HSRP? Alright, and their times. What are the different states and time? We have the initial, we have the learn, we have the listen, we have the speak, and when we have the standby. Now, the initial is a state that is entered through a configuration to change or when an interface first becomes available. Okay, once an interface first becomes available, it goes to the initial stage or state. Then learn is when the router has not determined the virtual IP address and has not yet seen a hello message from any active router. So it's still a new router in place. Listen is the router knows that the virtual IP address, but the router is neither the active router nor the standby router. It listens for the hello message from the other routers before it takes its decision. Speak. The router sends periodic hello messages and actively participates in the election of the active and or standby router. Okay, so they do election process. Then standby, the router is a candidate to become the next active router and sends periodic hello message. All right. So that is that about FHRP redundancy protocol. So let's launch a packet tracer. Let's launch a packet tracer to try that particular activity. All right. So we have our packet tracer. Okay. So let's put it this way so that we can run. Okay. Now it says that note the I-net router is not present in the internet cloud and cannot be accessed. All right, no problem. That is this one here. This packet tracer activity, you will learn how to configure hot standby router protocol, HSRP, hot standby router protocol, to provide redundant gateway devices to host on LAN after configuring HSRP, you will test the connectivity to verify that the hosts are able to use redundant gateway. Okay, if the gateway devices become unavailable. All right, so configure. What we're going to do, we're going to configure HSRP, hot standby router protocol. We're going to configure HSRP standby, and then we're going to verify the operation. So that's the packet tracer that we're going to do. All right, so let's see the scenario. Spanning tree protocol provides loop-free redundancy between switches within a LAN. However, it does not provide redundant default gateways for end user devices within the network if a gateway router fails. So FHRP Redundancy Protocol provides redundant default gateways for end devices with no additional end user configuration necessary. By using FHRP, two or more routers can share the same virtual IP address and MAC address and can act as a single virtual router. So hosts on the network are configured with a shared IP address as the default gateway. So in this packet tracer, you will configure Cisco Hot Standby Router Protocol, which is an FHRP. You will configure HSRP on router 1, which is this guy here, router 3, which is this guy here. So we'll configure HSRP here and here, which serves as the default gateways to the host on LAN 1 here and LAN 2 here. So when you configure HSRP, you will create a virtual gateway that uses same default gateway addresses for hosts in both LANs. So if one gateway router becomes unavailable, the second router will take over using the same default gateway address that was used by the first router. So because the hosts on the LAN are configured with IP addresses of the virtual gateway as default gateways, hosts will begin to regain connectivity to remote networks after that. So that's the scenario we have. So let's go straight into it. So first of all, we need to verify the path to reach the web server. Where is the web server? This is the web server here. And where is PCA? This is PCA. So how does our traffic get to to this web server? Is it going to follow switch 1, router 2, internet? Or is it going to go switch 1, router 3, router 2, internet? What is it going to do? Or is it going to go switch 1, switch 3, router 3, router 1? Or how is it going to move? So we're going to test that. And to do that, we use the traceSat command. Look at it. TraceSat. The traceSat command is the command we use to check the path in which your router takes to a destination. For instance, let me launch my command prompt. Let me show it to you guys. For instance, if I say traceSat google.com, what it's going to do is that it's going to check from my system now, from this my system, which path is going to, so this is my default gateway, then which path is it going to follow? It's going to follow, this is the IP address of my router, gateway of my router, then from my router, that's my ISP, sorry. Then from the ISP, it goes to another router in the ISP, then it goes to another router, so it continues to trace the route. So the route is doing now is checking every gateway as it is tracing until it gets to Google, and that is it. So it's the same method we're going to use. We're going to use traceSat to 209.165.200.256, which is our web server here. So from PCA, we want to trace how will our traffic get here. So we come here, come to command prompt, and we run the command. All right. So now let's see where it goes. So it goes to 192.168.1.1, which is the gateway. We're going to find out whether this is 1.1 or here. So it goes to 10, from there it goes to a 10.1.1.2 network, then it goes to 10.100.100.2 network before it gets to our destination. So we are going to find out the 10, the, the, the 192.168.1.1. Let's see our topology. So 192.168.1. All right, so this is the virtual. Look at it. The virtual is in switch 1. Where is switch 1? Default gateway. Sorry, the default gateway. Coming. Okay, 1.1. Where is 1.1? This is 1.3. 192. Okay, so the one. Aha, look at it here. Look at it here. All right, so it's in router 1. This is the 1.1. So our traffic came to switch 1 and went to router 1. Then where did we say it follows? Then it went to 10.1.1.2. Where is 10.1.1? Look at it, 10.1.1.2. So it went to router 2. So from here, instead of coming here, it went to router 2 here. Then from there, it went to 10.100.100.2. Where is 10.100? Look at it, 10.100.100 network, which is the internet here. Okay, so our traffic came to switch 1, router 2, internet before it came here. Okay, so that is what they asked us to verify. So we have verified. So which devices are on the path from PCA to web server? Use the addressing table, of which we just did. Now, step 2, trace the path to the web server from PCB. All right, from PCB we are to trace the same, run the same command from for PCB. All right, so PCB came to 1.3. All right, then let's see. Okay, all right, it came to 10.1.1.2, then 10.100.100.2 before it came to an end. So let's check who is 10.192.1.3. 192.168. This is 1.1. This is 1. Where is 1.3? 1.3 is the default gateway for PCB. Alright, so I guess, aha, look at it here. It's router 3. Okay, it's router 3. So the traffic from here, then came here before going to the internet. Okay, so observe the network behavior when router 3 becomes unavailable. All right, when router 3 becomes unavailable. So what we're going to do is select and delete the two from the bucket tracer bar and delete the link between router 3 and switch 3. So we'll delete. All right, so we have done that. So open the command prompt from PCB and execute the tracer command again. So this is PCB. So we run the command. Remember, this is where it came from 1.3 as its default gateway to 10.1.1.2 to 10.100.100.2. So let's run it now and see what we've got. Okay, because we have taken away a particular link. This is the link we have taken away. We have taken away the link from switch 3 to router 3. All right, so let's watch and see the behavior of our traceback. Okay, first time out. Okay, okay, so we are having request timeout. Okay, so running again. So we're having request timeout because this link is down. So our traffic is supposed to come to this switch here. and come to this router here and then continue its traffic. So I don't know why it's giving me request timeout. We are going to find out very soon. Okay, so let's see. So while that is still running, let's follow the instruction. This is open the command prompt and execute the traceroute command to the web server as the destination. Compare the current output with the one we did in step 2. What is the result? Alright, our result is request timeout, request timeout. But what we're hoping to see is that traffic will come to router 1 and goes out this other way. But for now, we have request timeout. So let's follow the instructions and see. So click the connection icon in the lower left in the PT, locate the cable straight through and connect. Make the connection types. Click switch 3 on G0/2 to router 3 and this. Okay. So we should come to connections, switch 2, and then this to this. Okay. So, alright, this is how we should do it. Click on this. Alright, we have done this. F says after the link and the connections are both green, test the connection by pinging the web server. Ping should be successful. Alright, so let's see. Is it green? No, it's not yet green. Alright, so we're going to, instead of doing traceroute, we're supposed to do ping. Ping should be successful. So our ping is successful. Alright, our ping is successful. Now, configure HSRP active and standby routers. So we'll come to HSRP on router 1. Where is router 1? Router 1, this is router 1 here. Okay. So on router 1, we are configuring HSRP. We enter global configuration mode by saying interface G0/1. Now, which interface is G0/1? And that is this interface. That's the interface connecting to the local area network. Okay, that's G0/1. And then they say we should specify the version of the HSRP protocol to be version 1, 2. So we'll just do standby version 2. Okay, then this says configure the IP address of the virtual default gateway. This address must be configured on any host that requires the service as the default gateway. It replaces the physical interface address of the router that has been previously configured on the host. So multiple instances of HSRP can be configured on a router. So you must specify the HSRP group number to identify the virtual interface between routers in the HSRP group. So this number must be consistent between the routers in the group. The group number is for this group is 1. Okay. So since we can have multiple HSRP virtual gateways, so we are using a group 1 to put them. So standby, remember we're still on the interface mode. Standby 1, that is the group number. Then IP, the IP address now. Sorry. The IP address that we'll be using now is 192.168.1.254. Okay. Right, so that is this now what we have just done. Now designate the active router, and how do you do that? By increasing the priority value. Okay, so if you don't increase the priority value, all the routers will take a default priority of 100. So but if you increase the value, you are rigging the election, something like that. Okay, So let's make router 1. Let's give it a priority of 150. So standby 1, priority 150. Okay. It says router 1 will operate as the active router and traffic from the two LANs will be used as the default gateway. So if it's desirable that the active router resumes the role when it becomes available again, again, configure it to prompt to preempt. Now remember the preempt that we are talking about is so that it will force it for re-election anytime a new router comes in. Okay, so configure that using standby 1 preempt. Right? So what will HSRP priority for router 3 be when it's added to HSRP? It should be what? 100. Anyway, we'll find out that. So configure router 3 as the standby. Configure router 3 interface that is connected to the LAN 2 and repeat only steps 1B and C above. That is, we should configure this and this. Okay, so let's follow the instruction. We have to do it on who? On router 3. So come to router 3. This is router 3, and we are going to do it on this interface. This interface, right? That's the interface that we are going to do. Okay. So configure terminal. Configure terminal. So we should configure router 3 interface that is connected. So we use the same steps we did. We go to interface G. I guess let's check the table. G0/1 router 3. Look at it. It is G0/0. Where it is? It's 1.3. So I think it's G0/0. Okay. So enter G0/0. Where is the observe? Okay. Yeah. So this is where we are. This is where we are. Yeah. G0/0. Okay. Then they say we should do step B. Step B is what? Standby version what? 2. Then step C says we should do what? Standby 1. IP is what? 192.168.1.254. Okay. Now the question is, why are we not coming to change the priority here? If we come and change the priority here, then there will the router 1 that we want to be the active router will not be the active router. You understand? So that is why we just have to just do that. So we have done this B and C. Now let's verify. Let's come to router 1 and do show standby. Okay. So show standby. Okay. Now let's see what we have got. The interface, yes, version 2 is enabled, and the state is what? The state is active. Okay, the state is active, and then look at the virtual IP address. So you see the virtual IP address in router 1 is the same virtual IP address in router 2. All right, and this is the hello time. This is the next preempt is also enabled. This is the standby router. Now you see the 1.3 is the physical IP address. Yeah, this is the logical IP address that is the same for both, but this is the physical. This is for 1.2. Then the priority for this router is what? 150. 150. All right. So we are good at that. So we come to router 3. Let's check. Let's check by using show standby. Show standby. Okay. All right. The state is what? Standby. It's not active. It's standby. And you see the virtual IP address is the same as router 1. And then is the hello time. Aha. Preempt here is what? Disabled. All right. Preempt is disabled. Were we asked to enable it? I don't think so. Okay, we'll check the instructions first. Maybe we have to enable. Then this is the active router 1.1. That is router 1. Okay, and then this router is standby with a priority of what? 100. Okay, so use the show standby brief on router 1 and 3 and view the status. So if I do show standby brief, okay, so it will give me the interface, the group number, the priority value, the state, standby state, the active router, which is the router 1, then the virtual, which is 4. All right, so it says change the default gateway MAC address for PCA, PCC, C1, and 3. Change the default gateway MAC address for PCA, PCC, C1, and 3. Which address should you use? Okay, now which address should you use? Now let me show you something. When we checked here, what is the MAC address? Take note of this MAC address. The active virtual machine, the MAC address is what? 0000 0C9F, then F001. Then let's come to router 3 and check. Let's come to router 3 and check. What is the MAC address? Can you see? It is the same 0C9F. In fact, let me put them side by side so that you see what I'm talking about. Let's see. Now, see the IP address. The virtual IP address is the same. Here is the same that is here. Then see the MAC address. Yeah, it's the same here. It's the same here. It's the same MAC address. It's the same IP address. Okay. So the question that we are being asked is coming. This is the MAC address. This one. Okay. So the question that is being asked says change the default gateway address for PCA, PCB, this. So the address, let's see, PCA, what's the IP address? So instead of 1.1, the gateway is going to be what? 1. This is 254. This is going to be the gateway. Okay. This is going to be the gateway. Sorry. Okay. This is the gateway for, okay. And then we say PC what again? PCC. PCC, what's PCC? PCA, we have done PCA, PC, I think they mean PCB. I think they mean PCB, we do PCC. So it's going to be the same gateway. Okay. Then switch 1 and switch 3. There's switch 1. This is switch 1. Alright. So the default gateway. And so if we do enable, so let's show IP interface grid. Let's see. No IP here. Good. So show on. I want to see what we have here. Look at it. IP default gateway is what? 192.168.1.1. So we are going to change it. Okay? We are going to change it. So I'm going to remove this one. IP default gateway. So I'll say no IP default gateway. This out. No. This is what I'm going to copy. I'll just put no and paste. Okay. Then I will now put the, the default gateway as what? 1.254. Okay. 1.254. Okay. So I will now come to switch 2. Then switch 2. Switch 3, sorry. Enable config T. I say no. In fact, let's check the default gateway here. Alright, this one, the default gateway is 1.3, right? Good. 1.3. So we'll put our 1.254, right? 254? Yeah, 254. Very good. Alright, so now you see verify the new settings using ping from both PCA and PCC to the web server. Alright, so we are going to ping the web server. This is the web server. Let me copy the IP address of the web server. Got it here. 256. Okay, so I come to PCA and then I run ping. Okay, ping. Okay, I have a reply. I come to PCB. I run the same thing. Okay, I have a reply. Okay, then what did they say we should do? Let's follow the instructions. Okay, was the ping successful? Yes. So now let's run our trace out. Let's run the trace out. Okay, trace out. Yes, this is successful. Let's run it from PCB. Trace out. Yes, it's successful. All right. So now let's make an active router become unavailable. So they say open a command prompt in PCB and enter the command traceat this. Does the path differ from the path before we configured? No, I think the path is the same. 1.1. The path is the same. Yeah. All right. So So break the link to router 1. All right, select and delete the 2 and delete connection router 1 to switch 1. This router 1 to switch 1. So, delete this. Good. So we still come to PCA. Now let's rerun this command and see what we've got. Okay, let's run a ping first. Ping, okay, ping is successful. Okay, sir. Good. Now I want you to check out this. The gateway here is 1.3. Previously it was what? 1.1. So it means that the redundancy has taken place. So before the tracer is 1.1, then 10.1.1.2. So here, what did we see? Look at it. 1.3, then 10.1.1.2, then 10.100.2, then that is it over there. So that means our redundancy is working. So if we break this one, it goes to the other way. Okay, so let's check our result and see what we got. Assessment. Oh, 10/10. Right, very good. So this is how to configure um, the FHRP redundancy protocol on our router. Okay. Let me see. Yep. That is for chapter 8, and let's go to chapter 9. Let's go to chapter 10. LAN Security Concepts. LAN Security Concepts. Now, the news media commonly covers attacks on enterprise network. Simply search the internet for latest network attacks to find up-to-date information on current attacks. Most likely, these attacks will involve one or more of the following. Either DDoS, in fact, we've gotten a report of DDoS very recently, last week, from a particular organization. DDoS attack, data breach, and then malware. Okay, most of these problems come in this particular form. And because of it, we need to find a way to secure our network. So various network security devices are required to protect the network perimeter from outside access. These devices could include our VPN, our firewall, next generation firewall, our network access control. These are devices that they are security devices that help us to prevent intruders from gaining access into the network. Now, endpoints are hosts, which commonly consist of laptops, desktops, servers, and IP phones. So anything that is an end device is an endpoint. Okay, and these endpoints have typically used traditional host-based security features such as antiviruses, firewalls, and host-based intrusion prevention systems. Okay, so these endpoints that we're talking about, these devices here, end devices or endpoints, sometimes they gain access to security, antiviruses or firewall and stuff. But things like camera, DVR, IP cameras, IP phones, you find difficult to get antivirus, but so rather you do intrusion prevention system. Now, the Cisco email security appliance is designed to monitor SMTP. All right, the Cisco email security appliance is constantly updated by real-time feeds from Cisco tools, which detects and correlates threats and solutions by using a worldwide database monitoring system. These are some of the functions of the email security appliance. It blocks known threats, so it synchronizes from the world database pool of security so that it prevents from known threats, uh, uh, remediate against stealth malware and evade initial detection, discard emails with bad links, block access to newly infected sites, and then encrypt contents in outgoing email to prevent data loss. That is Cisco email security appliance. All right, we have looked at endpoint protection. All right, what things that we need, the endpoint, then the email security appliance, and then now let's look at the web security. All right, so the web security appliance is a migration technology for web-based threats. It helps organizations address the challenges of securing and controlling web traffic. The Cisco Web Security Appliance combines advanced malware protection, application visibility and control, acceptable use policy controls, and reporting. All right, so the Cisco Web Security Appliance provides complete control over how users access the internet. So you filter maybe based on access list or based on web or based on content or URL. Right? So the web security appliance performs blacklisting of URLs and filtering of malwares and scanning of URLs, all to protect from web. So there are many access control, authentication with a local password. Many types of authentication can be performed on networking devices, and each method offers varying levels of security. Like when we were configuring our router, we use a line protocol with good password. When we configure SSH, we are putting security. And these are ways to do local authentication passwords. All right. Now, the local database method has some limitations, and the limitations has the user account must be configured locally on each device. So if you have 10 routers, that means you must configure the same login details on each of those 10 routers. All right, and then the method provides no fallback authentication method. So there is an alternative. There's what we call the triple A. Authentication, authorization, and accounting. All right, and it is a way to control who is permitted to the network, that is authenticate, what they can do while they are there, authorize, and then to audit what actions they perform accessing the network, that is accounting. All right, so local and server based are the two methods of implementing this particular AAA. The local method is method stores the username and password locally in the network, maybe on the Cisco router or whatever. All right, and users authenticate against the local database. So the local AAA is ideal for a very small network where your users are not very many. But we have a server-based AAA authentication. With the server-based method, the router accesses a central AAA server. The AAA server contains username and password for all users. The routers use either remote authentication, dial-in user service, that is radius. We call it radius server. It's very common, all right? Especially when you're using reporting and things like that. Remote authentication, dial-in user service, or terminal access control access, terminal access controller access control system, TACAS, protocol to communicate with the AAA server. Okay, so when there are multiple routers and switches, server-based AAA is more appropriate. So AAA authentication is automatic and does not require users to perform additional steps after authentication. Authorization governs what users can do and cannot do on the network after they are authenticated. So authorization uses a set of attributes that describe the user's access to the network. So these attributes are used by a AAA server to determine privileges and restrictions. And then the accounting collects and reports data usage, all right, and gives account of what the person used the network for. The primary use of accounting is to combine it with the AAA authentication. All right, so the AAA server keeps a detailed log of especially what the authenticated user does on the device. All right, 802.1x is a standard is a port-based access control and authentication protocol. This protocol restricts unauthorized workstation from connecting to LAN, okay, through publicly accessed switch ports. So the authentication server authenticates each workstation that is connected to the switch port before making available. So this one is done on the switch, and then it authenticates. All right. So layer 2 security threats. Layer 2 basically functions on data link and it deals with frames. All right. So network administrators routinely implement security solutions to protect the elements in layer 3 up through layer 7. They use VPN, firewalls, IPS devices to protect these elements. However, if layer 2 is compromised, then all the layers above, are also affected. All right. So, if, for example, if a threat actor with access to the internal network captures layer 2 frame, then all the security implemented on the layers above would be useless. Okay. So, what are the type of attacks or the categories that are likely to face? The MAC address table attack, one of which includes flooding of the table or altering the content. Then the VLAN attacks to include VLAN hopping and VLAN double tagging. Then DHCP attack to that one has to do with DHCP starvation, to starve the clients from getting IP addresses. Your DHCP server is working, but your clients are not getting IP addresses. Then the ARP attacks, address resolution protocol attacks, which includes the ARP spoofing. All right. Then you have the address spoofing attacks, and then you have the STP attacks. Now, all these categories can exist on the layer 3 or layer 2. Sorry, they exist on the layer 2, and so they're important. So, how do you mitigate against those problems? All right, one way is to do port security. If you enable port security on your switch, it will prevent people who do not have access who are not authorized to gain access. It will also shut down the port if there is a violation of any rule that you have set. Okay, so you can do port security, you can do DHCP sniffing, you can do dynamic ARP inspection, and then you can do IP source guard. IP source guard. Now, port security prevents many types of attack, including MAC address flooding attacks and DHCP starvation. And then DHCP spoofing prevents DHCP starvation and DHCP spoofing attacks. Then dynamic ARP inspection, DAI, prevents ARP spoofing. And then IP source guard prevents MAC address and IP address spoofing. All right. So let's look at MAC address table attack. This is the MAC address table. This is how it looks like of the switch. All right. If you just say show MAC address table, this is what you're going to see. Now, all the MAC address table have fixed size and constantly the switch can run out of resources in which to store MAC addresses. So MAC address flooding attacks take advantage of this limitation by bombarding the switch with fake source MAC address until the switch MAC address table is filled. What we are saying is that how does the switch populate this particular MAC addresses? It does flooding, and then the one that responds, it documents it. All right. So the MAC address table flooding attack, what it means is that it makes the switch document the wrong MAC addresses. So the MAC address table will be full with the wrong MAC address. So if a packet comes or if a frame comes, it will show that the destination is not within the table. So it will now flood it to all the ports and send it across. It will flood it and it continues to do that. Okay. So how do you mitigate about it? What makes tools such as knockoff of so dangerous is that the attacker can create a MAC address table overflow and quickly and very quickly. All right. So to mitigate the MAC address table overflow attacks, network administrators must implement port security. All right, which will only allow a specific number of source MAC addresses to be learned on a port. The port security is further discussed in another module. So in LAN attack, we have VLAN hopping attack, VLAN double tagging, DHCP starvation, and DHCP. So now let's look at each one of them. What is this VLAN hopping? The VLAN hopping attack enables traffic from one VLAN to be seen by another VLAN without the aid of a router. Okay, so it enables, on a normal day, the content of one VLAN should not be able to be seen by another VLAN, except it's a layer 3 switch that has been configured to do that, or there's a presence of a router. So VLAN hopping does that. So the threat actor configures the host to spoof the 802.1 queue and the Cisco proprietary dynamic trunking protocol, all right, signaling the trunk to be able to. So, for instance, this guy is on a particular VLAN and he wants to access the server on a different VLAN, so he does VLAN hopping so that he can now enter the other VLAN. Okay, so that's VLAN hopping. Then double tagging. A threat actor in specific situation could embed a hidden 802.1 tag inside the frame that already has an 802.1 key tag. So this tag allows the frame to go to a VLAN that the original 802.1 key tag did not specify. So these are the steps that we have. So the tagging, when you have a VLAN, the traffic that passes through, there are tagged traffic, there are untagged ones. If the traffic is tagged with a particular VLAN, it goes to that VLAN and no other VLAN. But if the traffic is not tagged, it goes through the trunk. So the trunk carries all the untagged traffic. So a threat actor in specific situation could embed a hidden 802.1 tag inside a frame that already has an 802.1 tag. This allows the frame to go to a VLAN that the original 802.1 tag did not specify. So it's like you have a VLAN, you overcoat it with another one, and then the message goes to the wrong destination. So how do you mitigate it? Disable trunking on all access ports. Okay, disable auto trunking on trunk link so that the trunk must be manually enabled. Be sure that the native VLAN is only used for trunk links. Okay, so DHCP messages. It does the discover, the offer, the request, and then the acknowledgement. All right, that is how clients request and get messages from their DHCP. So how do they get starved or attacked? The whole idea is that the goal of this attack is to create a denial of service for connecting clients. So DHCP salvation attack requires an attack tool such as Doubler, and has the ability to look at the entire scope of the leases of the IP address and try to lease them all. Specifically, it creates DHCP discovery messages. Alright, so it makes the router to lease the DHCP server to lease all the IP addresses so that no client is going to get. Now, ARP, Address Resolution Protocol attacks. Host broadcasts ARP request to determine the MAC address of a host with a destination IP address. So all hosts on the subnet receive and process the ARP request. The host with the matching IP address in the ARP request ends the ARP reply. So an attacker can send a gratuitous ARP message containing a spoof MAC address. A spoof MAC address is it's like you pick a particular MAC address that does not belong to you, and you are using it so that the system will accept it and understand that you are safe. All right, so it's put a spoof MAC address to a switch, and the switch will update its MAC address table accordingly. This typical attack, the threat actor sends unsolicited ARP replies to other hosts on the subnet with the MAC address on the threat actor and the IP address of the gateway. Okay, so the point here is it picks a MAC address that is not real, or it copies the MAC address of a different particular system, and it makes the switch believes that the MAC address is using is correct. So address spoofing attack. IP address spoofing is when a threat actor hijacks a valid address of another device on the subject or uses a random IP address. So IP address spoofing is difficult to mitigate, especially when it is used inside a subnet in which the IP belongs. So MAC address spoofing attacks occur when the threat actor alters the MAC address of their host to match another known MAC address of the target host. The switch overrides the current MAC address table entry and assigns the MAC address to the new port. It then inadvertently forwards the frame destined for that target host to the attacking host. So when the target host sends traffic, the switch will correct the error, relegating the MAC address to the original port. To stop the switch from returning the port assignment to its current state, the threat actor can create a program or script that will constantly send frames to the switch so that the switch maintains the incorrect or spoofed information. There is no security mechanism at layer 2 that allows the switch to verify the source MAC address, which is what makes it so vulnerable to spoofing. Now, how about STP attack? It says here that network attackers can manipulate the STP to conduct an attack by spoofing the root bridge and changing the topology of the network. Alright, attackers can then capture all traffic for the immediate switch domain. Wow. To conduct the STP manipulation attack, the attacking host broadcasts STP bridge protocol data unit (BBDU) containing configuration and topology changes that will force spanning tree recalculation. So the BPDU sent by the attacking host announces a lower bridge priority in an attempt to be elected as the root bridge. So this STP attack is mitigated by implementing BPDU guard on all access points. So BPDU guard is discussed more detail in the other talks. How about CDP recognizance? CDP is Cisco Discovery Protocol, and it's a protocol that helps you within your network to be able to see other Cisco devices that are on the network, and usually it runs on layer 2. All right. So this kind of attack, basically it enables all Cisco devices by default is enabled. So network administrators to use CDP to help configure and troubleshoot network devices. CDP information is sent out CDP enabled ports in periodic unencrypted unauthenticated broadcasts. So CDP information includes the IP addresses of the devices, the iOS software version, the platforms, the capabilities, and the native VLANs. So the device receiving the CDP messages updates its CDP database. So to mitigate against this, you disable your CDP globally. You only enable it on the interfaces that you want to run. Okay. So that is the end of that. So let's do one packet tracer activity for the LAN. All right. So I think this is a way to draw today's curtain. This is thank you so much for attending, and I believe that you understand today's class. If you have questions, you can always post it on the forum, and then for other